Hello everyone. Yesterday we talked about entropy. Today we're going to talk about qubits. Before I get to that though, I want to address Mike Bailey's comment. So what often happens is that I'll get like a synchronicity with a meme that sort of answers whatever question that I'm having. So yesterday on my Facebook feed, this meme popped up to kind of address Mike Bailey's comment, and at first I didn't really know exactly what to say about what he was asking. So if you imagine that her eye here is like a light source, and then it's sending out these rays. So you can think of that as like lasers. So if you suppose that her eye here is sending laser beams, then you can see that for the same amount of radians of displacement close to the light source, you're covering a lot less distance than when you're further away. You're covering more distance per radian, right? So so for 1 radian you get more arc further away from the light source than the arc that you get closer to the light source. Okay? So basically Mike's comment, the answer to Mike's comment is, so if you imagine that these are laser beams, and let's say I put like an object in front of the laser beam, and I put it near the light source, then you can see that it would cast a shadow over here, right? So then if I were to take that object that's close to the light source, and let's say I rotated it at like 1 radian per second or something, then if I went far enough over here, if I went far enough distance, then the question is, the shadow that object would cast, could the shadow break the light speed barrier? Because we all know that matter isn't supposed to be able to move faster than light. But it raises the question of, is it possible, could a shadow move faster than light? Well, that's a good question, right? And then furthermore, addressing his comment, supposing that the shadow could move faster than light, and then if you think about the fact that the shadow obscuring the light is giving you information, which is what we were talking about yesterday. We were talking about information. So if the shadow is giving you information about the position of the object that's obscuring the laser, so the shadow is giving you information. Now, is that information propagating faster than the speed of light, since the shadow would be propagating faster than the speed of light? Okay, so that's a good question. So go ahead and leave me some comments in the comment section about what you think the answer to that question is, because we all know signals shouldn't be able to pass the light speed barrier, right? Matter should always be moving at sublight, and information being conveyed should require some sort of signal with which to convey that information. So is the possibility that darkness can move faster than light sort of breaking the light speed barrier? So that's my question for you. I want you to think about that and let me know what you think the answer should be. And I always love when when Facebook gives me visual information on a question that I'm having. That's always nice. Okay, so, and I believe that I answered all of the other comments in text. If I didn't get to yours, you know, feel free to remind me. But I'm pretty sure I covered every comment in some form. And that was the only one that kind of gave me a moment where I was like, oh shit, you know, like, I should probably think about that for a minute, because that's a good question, right? Okay, so qubits. So I wrote out a couple equations, starting with the wave vector for a two-level system. So there's two levels. So this is the equation at the top. God, I hate how the camera is like reverse of everything. So this equation here for this wave vector, this is a two-level system, and then you can think of the 0 as like a classical bit in your computer, and then you can think of the 1 as a classical bit in the computer, and then you know that that for like text files or image files, you have definite bits, right? So like your bits are definitely 0 or they're definitely 1, right? And then what we talked about yesterday is how if you're breaking encryption, then you can represent the bits in terms of Shannon's entropy here. So you can represent the bits in terms of Shannon's entropy if you are breaking an encryption. Okay? And that's what we talked about yesterday. So you can go back and watch that video to catch up. And so for a two-level system, what do you think the Shannon's entropy would be for this two-level system of psi here? So I wrote out an equation for the state vector, and here I also included a phase. A lot of times with quantum computing, which is kind of what we're getting into here now, with quantum computing, a lot of times we'll just have like a minus, you know, or just like not even worry about phase. But there's always an option to also have a relative phase between the two bits. Now, this differs significantly from a normal bit that you use every day in your computer, because here you actually have a superposition of 0 and 1 bits. So in some sense, psi, this wave vector for psi here, this is kind of, in a sense, both a 0 and 1 bit at the same time. Now that gets into some dicey issues, because like we talked about yesterday, the uncertainty principle, and how we can't really know if it's a 0 or a 1, right? Until we actually measure it. And when you do measure it, I wrote out the probabilities. So little p, this is the probability of measuring the qubit. Well, I'm calling it a qubit. I'll just call it that, even though I'll explain in a minute. So you measure the qubit, and the probability of measuring a 0 is p, right? Now it's either a 0 or a 1. So what would be the probability of measuring a 1? The probability of measuring a 1 is 1 minus p, right? So those are your two probabilities. Those are your two probabilities for what to measure if you were to measure the bit. And once you measure the bit, then it collapses into a bit that like a classical bit, right? A 0 or a 1. So then before you measure it, it's a superposition of 0, 1 bit. Okay? Now, I'm thinking of it as both the 0 and a 1. And we talked about yesterday with the uncertainty principle, in a sense. It's kind of both. I mean, it's kind of neither. Also, like it's neither 0 nor 1. Now, when I'm thinking of it in terms of interference, now when I use the quantum interference, then I'm thinking of it in my mind as both a 0 and a 1, and then the two bits are allowed to interact with other qubits. So in that sense, both of the possibilities have some tangible reality, and when you're allowed to cross qubits like that, I've actually been thinking about this. Not only is it both a 0 and a 1, but the qubit is sort of like on two timelines, I guess. You could think of it as like multiple timelines, and the qubit is occupying the 0 timeline and it's occupying the 1 timeline, and it hasn't collapsed. So in a sense, it's kind of both at the same time, because prior to collapse, you could think of it as occupying both bits. Now, the Copenhagen interpretation is closer to its neither. However, I'm starting to feel like with the direction that quantum computing is going, I'm kind of feeling like rejecting the Copenhagen interpretation in favor of the multiple timeline interpretation of the superpositions. And the relative phase phi in the qubit, that can help you track interference also. Now, what I want to talk about, I don't know when, but what I want to talk about is how you can use these qubit states to crack RSA encryption, assuming that you have enough of them. I mentioned yesterday it's like in the order of like megacubites to break RSA encryption, so to do it with brute force and using definite 0 or 1 bits, it would take millions of years to crack RSA. Now, because the quantum superpositions allow you to occupy megabytes worth of the vector space at the same time, basically you can try out all of the combinations simultaneously in a single cycle. Now, with breaking RSA, it's not going to be like a deterministic algorithm. So, in a single cycle, the qubits, they're running through all the entire vector space of possibilities, and you're looking for that one combination that breaks the encryption, right? So now you can run through everything, but it doesn't collapse until you measure it, right? So what you have to do is you have to sort of bootstrap the interference of the qubits with each other, and then you have to cycle it through multiple times, and then what you want to do is you want to use that interference to raise the probability amplitude of the numbers that factor the encryption, and you want to gradually raise those probability amplitudes every time you do a cycle. And then if you do enough cycles, then the statistical distributions are going to kind of peak around the numbers that crack the encryption. And so basically you do like an iterative cycle, and that's kind of like a brief rundown on how to crack encryption using quantum computers. And you're going to be using these type of qubits, and every time you run through, it changes those p values, and you're going to be changing the probability amplitude of the combined quantum state. So now, how do we actually combine quantum states here? So I wrote an example for 2 qubit states. How to combine them? Well, so each one, psi 1 and psi 2, those are some combination of 0, 1 bits, right? So when I multiply them using a tensor product, then I combine the 2 qubits together, and then I get some linear combination of these 4 over here. So you have 0, 0, 0, 1, 1, 0, 1, 1. So basically, when I tensor 2 of these qubits, then I end up with a superposition of 2 bits, right? And then you can kind of see that I could just continue this process indefinitely, and I could get like a byte with 8 qubits, and 8 qubits, like a Q byte, is going to hold a lot more information than just your standard byte, because here you have a superposition of all of the possibilities of byte instead of just a byte, right? And all you need is 8 quantum bits to hold a superposition of all possibilities of bytes, right? But remember, you can't if you read the bit, then it's going to collapse, and then you're going to get a byte, right? So if you read the quantum byte, then you'll get a classical byte. So you have to leave it as a superposition, and you have to instead do computation using the relative frequencies of the qubits, and that's what you're going to be doing the computation on. So you can see that the most effective quantum computer would most likely be a hybrid system where it uses like a normal supercomputer combined with a quantum computer. Now, even though quantum computers are theoretically universal, you're not going to get peak efficiency. You're not going to get peak efficiency unless you split your code up. You want to split your code up into the quantum bits and then the classical bits, and that's how you're going to get peak efficiency on your algorithm. Even though quantum computers are universal, there's no need to use them to solve problems that can be accomplished with a normal supercomputer. Yeah, so we're discussing quantum computing. The main hi Kobe. Yeah, the main topic is qubits, and qubits are used for quantum computing, right? And hi Ruzel, good evening to you as well. For me, it's the afternoon. Okay, so those are the comments that we have so far. Yeah, keep those comments coming. Okay, so we're talking qubits now. So this is like a general. This is like a general 2-level system, quantum wave vector. That's a general 2-level system, 0 and 1 bits. And then also for electrons, you can have like an n-level system if you're dealing with energy, right? So with electron orbitals, you don't just have 2 possibilities, right? You have like the orbitals, and each time you go up an orbital, you go up in energy, right? And then from there it splits even further. At each energy level, you have degeneracies. So in a lot of like quantum situations, you're going to have like n levels, right, or n quantum superpositions. So now the qubits is useful because we already have a bunch of physics worked out for binary. So if we can program our quantum states using binary, we already have like a ton of math and we have a ton of physics that can go with that to do qubit binary computations. And also the theory that I'm developing for emergent gravity, it uses entropy in binary bits. Now, does that mean that reality is programmed in binary like a computer? The preliminary results seem to indicate that it is, but you kind of have to wonder if I'm like, because yesterday we talked about how with entropy the scale factor is in a sense arbitrary. So that arbitrariness might be creeping into the theory, and then we're basically writing the entire theory in binary, when in reality we could write the theory in any base that we want, right? That is a possibility. But the numbers certainly check out. If I make certain assumptions that we're going to discuss, if we make certain assumptions that we're going to discuss in these videos, the binary qubits work out nicely. So there's a good chance that the physics reality is written in binary code. There's a good chance. So yeah, that's pretty heavy. And yeah, Kobe, it is a tough one. So so that's another thing for you to think about, and leave me some comments on what your thoughts are. Is reality written in binary code? Right? That's a good question, because I've been pretty successful at writing gravitation in binary code. I've been extremely successful at that. So it would seem to indicate, but it's certainly open to debate, especially considering the last video that we discussed. Okay, let's see what other comments we got. Oh, nothing yet. Okay, yeah, so that is a tough one. Now, where was I with qubits? Yes. So this is what I typically think of as a qubit. So if the probability of 0 or 1 is 1/2, so it's like a coin flip. So if you set your 0 in one probability here, the root p, if you set that to 1/2, then and I can also set the phase to 0, because whatever. This is just an example, right? We're just doing an example. If I set the phase to 0, and then the probability of 0, 1 bit to 1/2, then I get my I qubit here. This is the quantum state, right? And then I wrote that using this exponent. Okay, that's another thing to read about if you're studying algebra still, is the exponents. So a square root on the denominator is the same as a minus 1/2 exponent, and I wrote it that way for the next step. And then what we talked about yesterday is that the probabilities being equal, 1/2, 1/2, that's somewhat related to being near a thermal equilibrium. So so in the emergent gravity model, what that would mean is that all of the bits on the surface are the same temperature, and each of the microstates of entropy has the same probability. Okay? And it's in thermal equilibrium with the ambient space, which I show in my article is actually not the case. But you can make like an approximation, right? So what I show in my article is that in a lot of cases you cannot assume that you're in thermal equilibrium with the ambient space next to the holographic projection screen, and in fact that flow of heat due to the temperature gradient, that flow of heat could actually be driving gravitation itself. Now, that aside, if you suppose that it is at thermal equilibrium, then the equation becomes a lot simpler. If you calculate the Shannon entropy of what we're calling 1 qubit, that's this state here, and if you go and you calculate the Shannon entropy, then you get 1 bit of entropy, right? Now we talked a little bit about how to combine these. Well, basically you just distribute, right? You just distribute the zeros and the ones. So if I combine n qubits, which is what we have in the emergent gravity picture, if I combine n qubits, then this would be the equation if we're near thermal equilibrium and each bit has the same probability, then that would be the equation of the state vector here. If we're near thermal equilibrium, right? And this is like the simple equation. Now I could write an equation. I didn't take the time to do it, but I know how. I could write it for n of these two-level systems. I could write a tensor. I could write a tensor, and in my mind I can see it. The notation hasn't quite come to me yet, but it's really close. And it would be similar to this, but more complicated, because you'd have a different p for each qubit. You'd have a different p, and then you'd have a different phase. You would have a different phase for each, different relative phase for each qubit, right? So it would be very similar to this equation. It just wouldn't be exactly the same. So here your tensor runs from the first qubit up to the n qubit, right? And you're taking the tensor product. And so this is the state vector that represents the qubits on the two-dimensional holographic surface. So that's what we talked about in the last video, right? So on the two-dimensional holographic surface, for the n bits of entropy, this would be the state vector if you're near thermal equilibrium. And going back to the first law of thermodynamics that we've been discussing, if I have a state vector, then I can calculate the entropy, right? And then if I can calculate the entropy, I can convert the units over to thermodynamic units. And then once I have an equation for the entropy, then I can use that here to calculate the change in heat. And then if I can calculate the change in heat from the quantum states, and the change of information, right? Then I can use that in this first law equation. I can use that heat term to try to calculate these other forces here. So next time I want to talk about the force on a particle. So what we're after here is gravity, right? We're trying to find the force of gravity that's caused by the entropy and temperature, and then that force of gravity causes a displacement. So that's what I want to talk about next. We already talked about pressure a little bit, but pressure and force are very similar. The pressure expands the volume, the force changes the displacement, so they're very similar. Okay, so that's where we're going. So do we have any questions? We covered qubits for about half an hour so far. Okay, if there's no questions, feel free to leave me some comments, and have a great rest of your day.